So now that we saw the four possibilities that occur with angle side side, let's kind of see it in practice and how we think about those pieces and think about our solutions. So here we're being given some information and I'm just going to put the pieces together to draw the triangle. I typically start with drawing the angle measurement, and again, if these aren't exactly correct, that's totally fine, especially with these ambiguous cases because it can be tough to draw without knowing. So I'm just going to draw a flat side, and then what we have 20 degrees, and let's see, a side length of 10. I don't know, maybe something like this. Yeah. And let's see, so that'll be gamma of 20 degrees. We have B of 10, so that's what we're having here. And then it's this idea that I want to draw this side length of 20 over here. And what I just need to check is because we're having angle side side, and I usually draw the number out here kind of floating before I graph it, because I want to make sure that what are the possible cases? Is it dropping as a right angle? Is it not even possible to draw it? Or is it landing out here? Or are there two possibilities? I want to think about all of those. Now this case right here is a case I kind of look for first, because this is a case where this side length that we want to draw is larger than the side length we have already. And that's the case where we just have one triangle. That was the last case that we looked at. That idea that if you dropped a string here that's a length of 20, it's going to go beyond over there, but over here, you'll get an intersection. So what I'm going to do is go ahead and just draw that side length there, and that's our side length of 20. So there's my angle side side. We're just going to have one triangle here to work with because of that side length of 20 being so long. Let's see. So what's missing? We're missing beta, we're missing alpha, and we're missing side length A. So we want to find all of those pieces to fill in the blanks. So in terms of law of sines, we have that pairing right there. So I know that sine of 20 degrees over 20 is equal to, and then I want to go to my next pairing where I have at least one piece of information. So here I know what 10 is, but I don't know what beta is. So I'm going to do sine of my unknown beta is equal to 10. And then we're going to solve. So to get sine of beta all alone on one side of the equation, I'm going to multiply both sides by 10. And we could reduce that down, or you can keep it messy. It's fine too, like 10 divided by 20, so that would be a half. So if we reduce that, it would be that sine of 20 degrees over 2, with how those would cancel out with each other. 10 divided by 20 would give us just 2. All right, to get beta, I need to take inverse sine of, and then sine of 20 isn't one of our special values, so this is just going into the calculator. So let's take a look at what this looks like. I'll go ahead and use this. Inverse sine, we're going to split it up. We'll have sine of 20 in the numerator over 2. And we get 9.85. And this is an angle measurement. So this gives us beta is 9.85 degrees. So that's a 9.85 degrees right there. Then to get alpha, we have two angle measurements now. So what I can just use is alpha equals 180 minus 20 minus 9.85. So we'll have alpha of 150.15 degrees. And then my last piece that's missing is the side length A. So with that, I need to go back to law of sines. So I'm going to use that sine of 20 degrees divided by 20. is equal to sine of, and I know my angle measurement of 150.15 degrees, but I don't know my value for A. So cross multiply and then divide, and you should get A equals 20 times sine of 150.15 over sine of 20. And that should give us a side length of 29.10 when we plug that into the calculator. So we get 29.10. And then I just do my quick little check of, let's see, smallest angle is across from smallest side length, largest angle is across from largest side length, so that looks good to me. All right, with this case here, we have an angle measurement of 60 degrees. And actually, yeah, that's good. Let's see, 60 degrees, something like this. Let's see, this is side length 6.2. It's kind of longer, I guess. Ooh, 60 degrees, maybe there-ish. Ooh, it's even further up like that. Close enough. All right, so there's 60 degrees. Then we have this side length of 6.2 for A. And then what I'm trying to draw is 5.5. So what I could see immediately is that 5.5 is shorter than the 6.2. So with that, I think of two possibilities. Well, I guess there's technically three possibilities. If 5.5 is shorter, there's the case where we end up with two spots that we can cross. We could end up with the case where it's exactly equal to the height, or we could end up with a case where it's shorter than the height and we don't even have a triangle that we can work with. Basically, what I need is the height of the triangle. I need to know what that height is to know what that comparison. Is it shorter? Is it exactly equal to? Or is it this case of, well, it's shorter than 6.2, but longer than H, and that'll give us those two crossings there. So with that, I'm going to find H as some kind of side work, and with that, it's taking sine of 60 degrees is equal to, and again, this is a right triangle here, take the opposite of H divided by the hypotenuse of 6.2. So H is equal to 6.2 times sine of 60, which we could just throw that into a calculator, and that should be a 5.37. So with this case, this is a 5.37, and I'm trying to draw a line that's a distance of 5.5. So this is a case where that 5.5 would go longer. So this is the two triangle case. We need to see an example of this together. So we're going to go through this. And with that, I'm going to erase all my markings for the height of the triangle there. And then I'm going to just draw these two cases, kind of like this-ish, something like that. All right, so this is 5.5, this is 5.5. So we have these two possibilities, and we have these two triangles. And what I'm going to do is I'm going to work with these two triangles separately, and the one that I start with, like I mentioned in the previous video, is the fact that our calculator is going to give us this angle right here. So I'm going to start with the big triangle. So we're going to have the two cases. We're going to have the big triangle with the 60 degrees and the 5.5 and the 6.2. And then we have the smaller triangle, and that's what I'll do second, which might look something more like this. So the 60 degrees, the 5.5, and the 6.2. And I'll even separate those up. And separate that. All right. So with this case right here, what we're looking for is we're looking for this value of alpha, and I'm just going to throw a little 1 next to it because we're also going to be looking for alpha over here It'll just be a different alpha. Same thing with gamma. Gamma 1, gamma 2. And then we'll have C as well. So we need to find those three pieces there. So using law of sines, we have the 60 degrees and the 5.5. So if I take sine of 60 degrees compared to 5.5, that should be equal to, and then I'm going to use this pairing of alpha with the 6.2. So sine of alpha 1 divided by 6.2, and then I'm going to solve. So sine of alpha is equal to 6.2 times 60 degrees, or sine of 60 degrees, which you could put in an exact value, but with these decimals, we're just going to end up in the calculator. So alpha is going to be the inverse sine of all of that. Let's go ahead, I'll show you plugging that into the calculator to make sure you have the format. So with that, I would go to inverse sine of, and then I'm going to separate up my fraction. And we're going to have a 6.2 in the numerator times sine of 60 over 5.5. And there's a 77.49 degrees. So alpha 1 is 77.49 degrees. So we just found this measurement. Then gamma just comes from that 180 degree rule. So we take 180 minus 60 minus 77.49, and that's going to be a 42.51 degrees. So up here, 42.51 degrees. And then with that, our last piece is to find C, and because, again, this is an oblique triangle, we need to use law of sines. So I'm going to need to use a pairing. I'm going to go back to the 60 degrees and 5.5 since those were exact values, and then use the pairing of gamma with C. So sine of 60 degrees over 5.5 is equal to sine of gamma, which was 42.51, over C. And then we just solve for C, so cross multiply, then divide, so that'll be a 5.5 times sine of 42.51 over sine of 60 degrees. And that should give us a side length of 4.29. So side length 4.29. I'm just going to run my check. Largest sides and angles, smallest sides and angles. So we solved the triangle. And we can take one deep breath of relief, but then realize that we have to do that all over again. Almost. It's a little shorter, but we still have a second triangle to solve. Another triangle that has the 60 degrees, the 6.2, and the 5.5. But we're going to be getting different alpha, gamma, and C. Now, what I mentioned in the previous video is that relationship that whatever angle measurement you get right here, this is going to be supplementary to that, meaning this angle plus this angle need to add up to 180 degrees. So what we can do is start off by finding alpha, but we don't need to use law of sines. What we can do is just take equals 180 degrees minus that first alpha that we found, which was 77.49. So this second alpha value is going to be equal to 102.51 degrees. So that's our obtuse one here. There's our 102.51 degrees. And then gamma is just going to come from the 180 degree rule for our triangles. So subtract 60, subtract it 102.51, and that'll give us gamma of 17.49 degrees. Which, let's see if I can fit that in there. All right. It's not too bad to get the angles, but then we do need to use law of sines once to get C2. So I'm going to use that sine of 60 degrees divided by 5.5 is equal to sine of gamma over C. And then just solving for C, so cross multiply, then divide. So we're going to have that in the numerator divided by sine of 60 degrees. And C1 will have a distance of 1.91. 1.91, and that makes sense that that's teeny tiny, with that tiny angle across from it, and then large angle with large side length. So that's the case where we end up with two triangles for our solution, and we need to completely solve both of the triangles in order to solve this equation that they're setting up for us. Given an angle and two sides, just seeing that there's two possibilities, so we're showing all possible solutions.